So yeah, I'll be talking this afternoon about sensor tasking and specifically ways that we can drive sensor tasking to favor observations for certain targets of interest. So I'll do a little bit of background on the sensor allocation problem, just a quick overview of the CPHD filter, which I'm using to represent the multi-object state. And then I'll go into the tasking reward function, which I'm using Run-E divergence, and I'll look at how to incorporate target priorities in there. And then I'll wrap up with a numerical simulation, looking at kind of a simple linear test case, and again for a bigger kind of orbit debris model. Okay, so in the sensor tasking problem, what we're looking at is what's the best way to make use of our limited sensor resources to gain information on this kind of large multi-object system. And we start with this idea that not every measurement opportunity is the same. So for example, if you're using angles measurements, and you've got a case where one object has most of its uncertainty in the radial direction that's going to be parallel to your line of sight, that's not really a good opportunity to get a measurement. Conversely, if most of your uncertainty is orthogonal to that line of sight, then that is a good chance to get a measurement, reduce the uncertainty quite a bit, and we want to kind of favor opportunities to do that. So what we want to do is look for those opportunities to be able to reduce the uncertainty overall for our problem, improve our state estimation, object characterization, our ability to predict collisions, and that's kind of the basic sensor allocation problem. So in addition, we need to be able to account for target priorities when we're doing this. Those can arise from any number of needs. So it could be user-defined, whether you're military or commercial. There's just certain objects that are inherently more important for your mission than others. They can be environmentally driven. So if we're predicting collisions or conjunction opportunities between objects, it's important to gather more data so that we can refine that prediction. And it can also be driven by tasking mode. So I usually look at this stuff in terms of we want to just maintain the catalog and do a good job with all of the objects. But for instance, if you're trying to do a calibration with one of your sensors, you might have a certain set of cal objects that you want to use, and you don't want to bother looking at anything else. So a quick review for the CPHD filter. This is just a way to keep track of multiple objects. It's got two components. There's the PHD function. This is your first moment of the multi-target PDF. It's representing the spatial density of objects in our state space. And then there's also the cardinality distribution, which is the probability that you have n targets present. So this is a discrete probability distribution that's keeping track of the number of objects for us. So we can set this up in sort of a recursive filter. We can begin with kind of your full multi-target PDF, break it down into these simpler functions for the PHD and cardinality, and then we have the equations that we can run a predictor and corrector to incorporate measurements and improve our estimate. In terms of tasking reward functions, there's a lot of different ways that we can go through and do this. So even just within using information gain reward functions, there's a lot of different options. The one that I use is Run-E divergence, but the idea with all these is pretty similar. So what we want to do is be able to compare two different PDFs. So if we have some kind of prior PDF, it's a little bit spread out, we collect a measurement, we know that it's going to get a little bit of a sharper peak, we're going to reduce the uncertainty, we want to be able to quantify how much we're doing that. So these different information gain metrics give us a way to do that, so that the larger the change in the uncertainty, the more information that we've gained, and we can use this to drive sensor tasking. So if we're always trying to maximize the information gain, we're going to be reducing the uncertainties for our different objects, and we're going to do a good job maintaining our catalog. The last piece I want to talk about is how to incorporate target priorities. So within the context of FIST or CPHD filters, we're going to use this tactical importance function, or TIF. So you can use this value. It's just a value between 0 and 1, and it's going to allow us to specify targets of interest. So within the state space, we assume that we just have some targets around. There might be a region in that space that's, for whatever reason, more important than others. So we can use this TIF to say, if it's in this region, these are objects that are more important that we want to do a better job keeping track of. What I've got shown here is kind of a sharp distinction. So the objects that are in this circle are ones that I care about, everything else I don't. This could also be more like a ramp, so that as objects get closer to some place in the state space, they become increasingly more important. You can kind of do what you like with this function. In terms of how it affects the PHD, again, that's the target density in space. So if we integrate the PHD, then we have our expected number of objects. We can get this sort of TOI biased version of the PHD function and the number of objects just by multiplying. And so then when we integrate it, you end up with the expected number of TOIs in that space. The way I actually implement the filter is using Gaussian mixtures. So I have this weighted sum of Gaussian PDFs to represent the PhD. You can take the sum of the weights to get the expected number. So I just go through and I multiply this by the TIFF for each object. So the way that I'm implementing this, I'll go through a little bit more when I get to the test setup, but I'm doing a very simple case here where I'm not going to use a full state-dependent TIFF. I'm just going to assume that I know all the objects a priori. I know which ones I want to be targets of importance, and I'm just going to set a value of tau for each one. Similarly, we need a cardinality distribution as well as a PhD, and so I'm just using a multi-Bernoulli as shown here. Okay, so to kind of summarize the approach, what we're going to do, we're using Rani divergence as this reward function. It's a function of both the PhD and cardinality distribution, including the TIFF. At each time, we're going to predict the distribution forward. We're going to consider a number of different sensor tasks. We can go ahead and simulate the measurements and the update that would happen with that, compute the expected information gain, and then we're just going to select the maximum value at each time. So it's just kind of a single step look ahead, maximum information gain. Doing this, we expect that it's going to drive tasks to reduce the uncertainty in the estimated target number and the spatial distribution. So we're looking to improve the PhD and the cardinality distribution. And the relative value of the TIFF is expected to drive sensor tasking to favor these kind of higher priority targets. So to test this out, the first test case that I looked at is kind of a simple linear motion model. So I've got the test set up on the left. What I did is I simulated two objects. They're moving at a constant velocity past a sensor. At each time, we're going to select one of those two objects to observe, and we'll get an angles measurement for it. Then we update the object state, propagate it forward to the next time, and do that all over again. So the first set of results that I'm looking at, I've set the value of tau for both objects to the same value, which is 1. So in this case, the two objects are evenly weighted. They're even priorities. We want to be able to observe both of them kind of evenly. So looking at the results, the top plot here is the trace of the covariance matrix for both objects. The middle is the expected information gain for each, and then the bottom is the object ID that we actually observed. So as you can see, it does actually alternate between the two objects. We're collecting information and reducing the covariance for both of them. At the final time, it's about the same level. And you can see the expected information gain for both is kind of decreasing steadily throughout as we're improving our estimate of the objects. And it's also kind of alternating back and forth, which is what's driving our tasking to alternate. So this is working about like what we would expect. So what happens when we start to reduce the priority for one object? So I took a look, keeping the priority for object 1 equal to 1 and changing the priority for object 2 to 0.1. I ran the same test case again. So in this case, it schedules object 1 preferentially, basically continuously for the first half of the test because the expected information gain for object 2 is very low. Starting at about the halfway point, it does begin to schedule object 2, but it's still kind of favoring observations for object 1. And then you can see this reflected in the covariance. We're doing a much better job estimating object 1 sort of throughout. The final test case that I looked at for this was just setting the value of tau to 0. So this is going to force the information gain for that object to be 0. We're just going to ignore it completely and spend our whole time observing object 1. So this is just sort of a simple look at it, seeing that we can use these information gain values and priorities to drive tasking towards another object, whether it's preferentially or if we want to have some kind of a tasking mode where we just completely ignore one object and spend all of our time observing the other. Okay, so to build this up a bit to a more interesting test case, I have this orbit debris scenario. What I did, I looked at building up a test case with 5 ground stations, and we're going to go look for geo objects. So I've got each ground station mapped out along with its expected field of regard. I'm going to have each sensor be active for 12 hours, take observations once every minute. They're going to be corrupted with Gaussian noise with 2 arcseconds in each direction. And there's also some misdetections and clutter in the measurement set. Finally, I'm going to be using that same sort of single-step information gain tasking that I was previously. In terms of the object sets, I grabbed a set out of the TLE catalog for a date in 2013. applied a few constraints to get geo objects, and I ended up with about 1,100. The simulation runs for a course of 24 hours, so we're just going for 1 day. And then what I needed to do was specify some TOIs. So to decide which objects are going to be my targets of interest, I said, I'll just take 10% at the beginning of this, kind of randomly select them throughout, and I'll designate those to be TOIs. So through the course of this whole simulation, I'm not considering any target birth or death. Nothing's going to appear or disappear or anything like that. I'm assuming that I know at the beginning everything that I need to know, and I know that I have these certain targets of interest defined as well. And so similar to before, what I'm going to do is I'll take the TOIs and I'll set the priority for them to 1, and then I'll vary the priority for the non-TOIs and see how that affects my sensor tasking. Okay, so the first sets of results I'm looking at on the left are for the case where all the objects are kind of evenly weighted. So even the non-TOIs have their priority set to 1. In the plot, all the gray lines are representing the individual position areas for each object. And then I've also got the averages plotted as well. So the black value is the average for all objects, blue is for TOIs, and then red is for the non-TOIs. In this case, with everything kind of evenly weighted, all those averages come out right on top of each other, which is what we'd expect. So there's no preferential treatment. Everything is just kind of being observed when it gets observed. On the right, I'm looking at a case where I've set the probability for the non-TOIs to a small value of 0.01. In this case, I didn't want to actually go all the way to set them to 0, just because I wanted to make sure that the sensors always had something to do. So in the case that there's no TOIs visible, there will still be some positive information gain tasks out there, and it'll still go observe some objects. But you can see that it does clearly favor scheduling the TOIs. So the TOI average is dropping down rather quickly, while the average is kind of decreasing much more slowly. At the final time for this one, the average position areas for the non-TOIs is much higher than it is for the evenly weighted case. So this just shows, again, reducing the non-TOI priority is yielding improved TOI errors at the expense of these non-TOI objects. So to take kind of a closer look at all the different cases, what I've got here is just the averages for the TOIs and the non-TOIs for the cases where I was changing tau from 1 down to 0.01. So on the left are the average TOI errors. You can see that the 0.01 case does the best. It kind of quickly converges to the best errors at each time. Those little steps down that it has throughout are when new sensors are coming online or coming active. So it gets a new set of objects that it can observe, and it's driving those errors down. Even still, all of the cases end up doing pretty well with this. And that's just because there's enough sensors and there's enough coverage, enough measurement opportunities that it's able to get good information on the whole catalog. But overall, the 0.01 case is still the lowest. On the right, looking at the non-TOI errors, again, most of the cases do pretty well. It's pretty clear that the small case, the 0.01, is kind of abandoning measurements on those non-TOIs for the sake of doing a good job with the targets that we're primarily interested in. And the other thing that I want to point out in this particular case, the 0.1 tau value actually does pretty well on both. So it's keeping up with the 0.01 on the left and kind of the tau equals 1 on the right. So in this case, it's to say that we could just kind of preferentially treat some targets of interest while still doing a good job maintaining our catalog with all the other objects out there. And the last one to look at is just some quick summary table. So this is just looking at some numbers on the objects that we detected, the number of TOIs detected, and measurement information. So the tau equals 1, the even case, does the best in terms of detecting the most objects. It does pretty well detecting TOIs. When you get down to the 0.01 case, it's detected the fewest unique objects, but it's actually the only one that detects all of the TOIs that we were going for. In terms of number of measurements, the 0.01 case gets the most overall, and it gets the most for TOIs. The reason that it gets the most total overall is actually any time that it's not going for a TOI measurement, it's going for a multi-object measurement. So anytime we have a multi-object opportunity as opposed to single object, that's going to be a higher information gain state. So whereas the tau equals 1 case is kind of spreading around and getting a lot of single object opportunities, the 0.01 is basically either getting TOIs or it's getting multiple objects at once. And then the final column is looking at the actual sensor time. So where the number of measurements includes some missed detections in it, I wanted to look at how much time is the sensor actually scheduling TOIs, whether or not it observes them. So in the first case, where things are pretty evenly weighted, about 10% of the objects are TOIs, and it's doing just a little bit more than that. Overall, the network is doing 17% of its time scheduling those, down to the case where you're at 0.01. And in this case, we were spending 80% of our time tracking those important targets and 20% just off gathering the rest of the catalog. So this is just to demonstrate that varying these TIFF values can produce a higher percentage of sensor time and more measurements for the TOIs. So to summarize, from the results, we can see that the Ragni divergence can be used to drive the sensor tasking to reduce our average state errors. The TIFF is providing us a way to incorporate these different target priorities in the reward function. It can be done state dependent. I haven't tested that case yet, but the results here show that you can use it to drive the sensor tasking, to get additional measurement and reduce the state errors for TOIs. In terms of applications, this is going to allow users to be able to define TOIs during catalog maintenance. It also provides a means to implement different sensor tasking modes. For example, if you're doing calibration and you just have a certain set of objects and you want to ignore everything else. And finally, you can use this to drive environment-driven tasking. So if you predict a conjunction or a collision or something and you want to gather more data on those objects, you can use this to kind of adjust the priorities and get more. So with that, I'd like to thank everyone, and I'd be happy to take any questions.
Questions for the speaker?
Yeah, great talk, Steve. Just wanted to know kind of where do you see the next step of the work going, and have you thought about maybe folding in probability of detection into the tasking?
Yeah, absolutely. Yeah, that's definitely up there. The next one, I think, is to also include labeled random finite sets, like Brandon's been working with. I think that's definitely a better step in the CPHD. And actually, I really like the previous talk as well with the Dempster-Schaefer stuff. So being able to switch between search and task mode and use that kind of thing. I think, yeah, there's a lot of stuff to do.
All right, it's a great pleasure to be here today giving this presentation for my colleague, Roberto Fafaro, who couldn't be here today. I'd also like to acknowledge my co-authors, Richard Linares from University of Minnesota, Marie Baja, and Ramona Wells, both from University of Arizona. All right. So this is kind of the typical slide. You've probably seen this graph a million times. The thing that I want to say about it is that our long-term goal at the University of Arizona is to be able to understand and predict the behavior of all these objects that we have in Earth orbit and beyond. This slide here shows an overview of an approach that we have for taking observations and using physics-based models as well as machine learning techniques coupled with Bayesian networks and ontologies to give information to decision makers. So our goal is to characterize and classify resident space objects, or RSOs, and it's been suggested by several people that orbital energy and angular momentum may be more useful than just the typical Cartesian state vector or orbital elements to identify classes of objects and associated patterns of behavior. And so what we're going to try to do here is use an extreme learning machine, or ELM, to characterize the relationship between sensor measurements and energy parameters, so energy and angular momentum, as well as states, such as the eccentricity vector and semilattice rectum, or SLR. So the ELM, it's not only has a cool name, but it's a single layer forward network, and it learns very quickly. And so what we did is we simulated 1,000 near-geo orbits and 1,000 GTO orbits, and we had measurements spaced at over about 2¼ days, 100 measurements per orbit, and so that spaced them at about 30 minutes per measurement. So then we trained the ELM to be able to predict eccentricity vector and SLR from measurements, and this is all in simulation at this point. The network itself used 2,000 hidden neurons or nodes when we are just considering either GEO or GTO separately. When we combine and try to look at both at the same time, then we use 3,000 hidden neurons. And so then we did training and validation. And so in the training phase, we used 800 data points. And then for the validation, we used 200 data points. Let's see. So this slide here, sorry that it's kind of hard to read. Hopefully you can see it much better in the paper. But what we have are results for the near GEO. And we have results for the eccentricity vector first component, second component of eccentricity, and the SLR. And the blue lines represent the training phase, and then the green lines represent the validation lines. And if this thing is working properly, all the black data points that come out of the ELM should lay right on top of either the blue or the green lines. And so in the case of the training, all the data points just lay right on the line. But then in validation, where we're trying to predict ahead or actually use the ELM in practice, it does really well. So most of the data points are right on top of the line. There's a few that don't, but for the most part, it works really well. So then we want to take this and then apply clustering to it in order to understand the behavior of the RSOs. And so we use the ELM to map sensor measurements into a feature space. And in this case, the feature space is the eccentricity vector and semilattice rectum space. And then we want to look and see how the RSOs cluster in that space and see if we can discover some patterns in the data. And listed here toward the bottom are 3 different preferred techniques for doing this clustering analysis. So this plot shows how the data clustered. So we have, in the blue, we have the GEO orbits, and in the red, we have the GTO. And so just from inspection, it's very easy to see how these 2 different kinds of orbits clustered very well. So on the plots, the SLR is in the vertical direction, and the 2 components of eccentricity are in sort of the horizontal plane. It turns out that we had a very simplified orbit model, so just 2-body gravity. So in real life, when you have perturbations such as solar radiation pressure, atmospheric drag, and things like that, we think that maybe the clustering won't be quite as obvious, and so in that case, we would use one of those 3 techniques at the bottom of the last slide. So now we're kind of jumping to a different topic. So now we're going to talk about how we uses space object behavioral ontology, which was discussed yesterday afternoon by my colleague Ramona Walls. And how do we use that to develop a Bayesian network? So when you have an ontology, you can use different ontology management systems such as Protégé, and they have these reasoners that are built in, and then you can do some reasoning. However, these reasoners, they do not handle uncertainty or probabilities. And so what we want to do is use the ontology to help us build a Bayesian network so that we can then do probabilistic reasoning. So this is how we approached mapping the SOBO onto a Bayesian network. So it turns out that an ontology and the direct acyclic graph from a Bayesian network, they look very similar and have similar structures. And so what we did is we transformed classes, instances, and properties from the ontology into nodes and links on the Bayesian network. And then once we had that, we're able to compute conditional probability tables to compute conditional probabilities of things we're interested in. And we used the two software packages to help us do that, Protégé and Netica. So we tried to exercise the approach that I just talked about with an example. What we were looking at was how do you compute the probability of collision between a group of active objects or active satellites and a group of debris. And so we started off with a pretty simple ontology that is shown toward the bottom here. And so on this slide, we have a little bit more of the details. So at the top, we have an object, and it has subclasses of satellite and debris. And then those subclasses are further broken down into active satellite, inactive satellite, and fragment. We also added a class for probability. So we have a probability class that has value and weight. And then below the line, we have an instance. So this is an instance of a inactive satellite. It has these different characteristics and the relationships between the pieces of the ontology. Then on the left, we have an event, which happens to be a collision that happened on February 10th of 2009, which some of you may remember that date because of the Iridium Cosmos. And so this shows the whole, the ontology and how that links to this collision event. So then, once we had that, then we were able to put together the Bayesian network and then pull out this conditional probability table, which again, it's kind of an eye chart. You'll be able to see it a lot better in the paper. This chart shows the final Bayesian network that was created based on the ontology. And so some of the benefits of this approach is that the ontology is going to change and grow over time. More objects, things are going to change states or where they belong in the ontology. And so the Bayesian network that gets derived from it can also adapt and grow or change as the ontology does. Another nice thing about it is that now we have a way to rigorously determine conditional probabilities that are based on the knowledge that we have based on the ontology. And then finally, another benefit is that we have now a semi-automated process to create the Bayesian network so that it's much faster and easier to create that than trying to do it manually. So the next step, we're working on using all of this stuff to perform a case study where we're looking at objects in geo and near geo and trying to assess whether they are or will comply with the IADC end-of-life disposal guidelines for geo objects or satellites. And so at the next AMOS conference, we hope to present all of those results to you, and so stay tuned for that. So thank you very much.
Thanks for the introduction. So I'd just like to acknowledge my co-author here, Roberto Fufaro from University of Arizona. And so what we're doing with this talk is there's a lot of talks about sensor tasking and management, and what we want to propose is solving that problem via reinforcement learning. So SSA, you've seen this chart many times. So the main takeaway from this chart is SSA is very important, and we want to be able to protect our assets, which requires us to understand and observe them, understand their behavior and predict them. But what we're really going after with this paper is we want to answer the question of how do we design an intelligent system to solve the challenges in space situational awareness. And what we're proposing here is let's try to use reinforcement learning. So this work takes the initial step towards that direction in developing an intelligent agent that can learn from its own experiences in solving SSA questions. So reason why we're looking at this is there's been a lot of recent success with these types of approaches with reinforcement learning. There's been a lot of popular articles in the media. For instance, this Nature paper, Google beat the world champion in Go with their AlphaGo program, and also has done very well in solving or playing commercial video games using reinforcement learning. And the real benefit of this approach is not the toy problems that have been solved, but is the idea of reinforcement learning. And the idea is that we have an environment that we try to predict with some learning model, and we have an actor that performs action on this environment. And over time, as an actor performs more and more actions on the environment, the actor gets better at doing this. So what we want to try to do is solve sensor tasking and management using this approach and apply that directly on data, and over time your network gets better at tasking itself. And there's a couple of benefits of doing it this way. As the previous talk mentioned, there are a lot of ways of defining the reward. So the objective of the sensor tasking and management can be defined in a lot of ways. Reinforcement learning actually allows you to define that in very broad ways. So as long as you can define a reward, basically if you do something, you get a reward. Doesn't have to happen instantaneously, it could be delayed. So my reward could be defined in terms of classification. I could tell the actor that I want to classify these two objects, and I have an algorithm to do it. Collect as many measurements as you can until you classify it. I'll let you know once you classify it. The previous talks that you've seen can't solve problems like this because you need to code the mathematical structure of how that reward influences the policy. And the benefit of reinforcement learning is we can do that in an end-to-end fashion. And there's success stories of that. The autonomous car is a particular success story. It's a very complicated scenario, the autonomous car scenario. So basically what we have in this scenario is we have a complicated world, and it's hard to hand code everything that happens in this world. And the world is observed with images and LiDAR measurements. And what the reinforcement learning approaches try to do is learn a mapping from raw data to action. And what that action in this particular case is steering angle and throttle and brake. And what we want to try to do is how can we apply that concepts from that field to space situational awareness? Where's the analogy? The analogy in space situational awareness is we have raw measurements. We're taking optical observations of satellites, and we want to output SSA data products. We might have higher level objectives that a commander might specify, and we want to define a reinforcement learning approach such that it provides a mapping from an action to achieve that objective. So there's a lot of similarities, and the main takeaway here is that SSA is fairly complicated, so trying to design an algorithm that can answer these broad natural language statements is very difficult. But designing this in a reinforcement learning approach could be a possible solution. Okay, And so just an overview of sensor tasking and management. There's different types of mission, and when you say sensor tasking and management, it might mean different things to different people. For instance, I might have the mission of collecting objects to maintain a particular large catalog or a subset of a catalog, or I might want to classify and characterize a new launch or a new object, and that might be my mission. And there's different objectives you can define. There's information gain that folks have talked about. Uncertainty reduction is a possible objective. Maximizing the mutual information is an objective. And expected information divergence. So there's a large set of objectives that you can define. And most approaches are dealing with myopic sensor tasking and management. And what that means is that at the current time step, I'm making the best decision. But those approaches really don't consider the long-term planning aspect. If I'm observing something with a high eccentricity, and if I don't get that object's, or for instance, a high area to mass ratio, if I don't get that object's uncertainty down right now, I'm not going to be able to reacquire it. So I'm better off observing that object instead of observing a geo-object. That problem is actually hard, and that's why a lot of approaches don't exist to solve that. Reason why it's hard is because the number of actions can grow with your time horizon. As if I take that time horizon forward, the number of possibilities can grow very large. So it's a tough problem. I'm not saying that we're solving it completely, but what we're talking about here is a way to get close to optimal for this complex scenario. Okay, so what are we trying to do? We have an environment. That environment is driven by some random process, and this is, for instance, unmodeled effects that influence our satellites. We have a reward, and that reward is our objective. And our policy is given some observation of that environment. And then our policy is allowed to influence the environment with some control. And we can formulate that problem in terms of a reward at time step k. And what we're trying to do is optimize this total reward summed over all time step k's over this parameter theta. What gamma is doing here is basically favoring rewards at the current time step, and this gamma value is less than 1. So rewards that happen in the future are less weighted in this formulation. And that's the general statement of reinforcement learning. How do I find this parameter theta? Okay, so what are we doing? So we have this environment that our state variable lives in, and at the current time step, we can take an action. Let's call that U0. And as we follow this path, we can take multiple actions to get to a final state. At each state, we receive some sort of reward. What reinforcement learning tries to do is it tries to model what is the total reward of a particular policy. Can I model that as a function? Given my current state, my current position, and an action that I might take at my current position, can I output a scalar value that tells me what is the total reward of following that policy from the current time step till the end? And actually what we can do with reinforcement learning is we can use the Bellman equation to write a condition for that function, and we optimize this condition. So we use this condition to solve for parameters in this value function that allow us to optimize over policies. And that is reinforcement learning in a nutshell. So we're just taking steps in the environment, and we're getting some sort of reward, and we're learning from those steps. And how do we do it? And for instance, in this case, we're proposing a deep reinforcement learning application. So what we do is we model our value function as a neural network. We model that as a general function that we need to fit parameters to that. And the best function to do this in terms of reinforcement learning is a multi-layered neural network, and we're calling that a deep neural network. And that represents our value function for a particular policy. That represents, if we follow this policy, how much return are we going to get? And how do we find a solution for that policy? We simply optimize that value function using stochastic gradient descent, which is traditional optimization approaches. So here are some equations just to describe what we actually do. So here is the equation I mentioned earlier. So this is the reward at time step k. And then there's a typo there. It's k plus 1. So if I go k time steps forward, I can write this reward function. And I can telescope the reward function or unroll it and write the rewards after time step k using this value function. So after time step k, I can write it in terms of the value function. Just the value function in terms of my position at k plus 1. And my action at k plus 1. And we can actually write a Bellman equation. This is a concept from optimal control in terms of this reward function. And the Bellman equation for reinforcement learning is given like this. And we solve for the value function by optimizing this Bellman equation. So we calculate what is the error in this equation. How far are we off from satisfying this equation? And that's our objective function. So that's it. So now we have this general function that maps from our current state and possible actions to our overall reward. So if you come to me and you give me a general reward, I try to learn this from experiments, okay? And what we actually do here is we actually implement something that's called policy gradient, which actually makes this approach a little bit more robust. And with policy gradient, we have a probability mass function that governs our policy. So we make our policy random and a function of this parameter, theta. So for any given action, we have a probability associated with that action, and that probability is a function of these parameters, theta. And we can optimize this policy by looking at the reward function or the expected value of the reward function using our probability description of our state, and actually manipulating this equation and using some identities, we can rewrite this expectation in terms of the log of this probability here and the reward. And there's a theorem that allows us to rewrite this statement in terms of this value function. So we have here our policy, which allows us to calculate the probability of taking a particular action, and our value function that I mentioned earlier, which estimates at the current state what is the expected total value if I perform this policy pi. And now we take a gradient of this and we calculate a gradient descent direction, and we can optimize our parameter theta using this gradient descent direction. And that's the reinforcement learning approach that we're implementing, and that approach is called the actor-critic approach. And essentially, our value function is a critic. It evaluates how well our actor is doing. So our actor decides to perform some action, and then the critic comes back and tells it, well, you know, this is how well you did with that action. And using this interaction between an actor-critic, we can actually take rewards and states from the environment and learn what this function should be in simulation. So what did we do for our simulation case? The font's not showing up very well here. We simulated a set of satellites using 2D two-body motion, and we simulated a planar angle measurement. Just for simplicity, we can go with a three-dimensional state. That's not too much for the approach to handle. And we need to define what our state is. So for this case, we want to try to estimate the orbits for a particular catalog. So for this case, our state is the PDFs of the entire distribution of satellites. And a simplified way of modeling the PDFs of these distributions is to assume that they're Gaussian. So our state is modeled in terms of means and covariances. And in this case, we took the diagonal of the covariance to model our state. And then we can propagate the mean and the covariance using our mean propagation and our covariance propagation equation. If we have some process noise, we have this extra term here. And then our value function for this case is represented, like I said, like a neural network, as a neural network. The first layer of the neural network has 200 hidden units, second layer has 100 units, and the third layer has 50 units. And our activation functions are these rectified linear units, which are basically linear functions if they're active and 0 if they're not, and that produces a nonlinearity. And like I said earlier, this reward function can be defined fairly generally. So this reward function can be defined whether or not you achieve the particular task. Or in this case, we define this as this sigma bar here is the maximum variance, average positional variance for any object in the catalog. So we want the maximum variance of any object in the catalog to be below a threshold sigma bar. If it's not below the threshold sigma bar, we give a negative reward to our agent. If it is below the threshold, we give a positive reward of 1 to our agent. So we're rewarding our agent only once it reaches this threshold. And as long as it's not below the threshold, the agent does not receive any rewards. Okay? And here's a simulation case of a 3-satellite configuration. We've done a larger number of satellites, but this is just to illustrate the policy on a simple case. So on this simple case, we can see that over these iterations represent the agent taking actions on the system. So one particular iteration is I let the agent observe the 3 satellites until it reaches its objective. So that's one iteration. And I repeat that over and over again. I let the agent play in this environment until the objective is reached. And then this is the average reward as the agent learns how to play in the environment. So over time, you can see this is about 1,000 iterations. The agent starts to get better and better and starts to approach a steady state value of what's the optimal solution for this particular problem. And what we can tell from this figure is that these rewards are somewhat random here. They're random for a couple of reasons. The agent is a random actor. So the decision it makes has some slight randomness to it. But I also generated the satellite orbits from a random distribution so the agent can learn a general pattern. So instead of learning a specific scenario, we give it a lot of variations of different types of satellites so it can learn how to solve this problem for any particular satellite. And then this is one simulation, one particular case. And as you can see here, the covariance, this is the sigma covariance of the 3 satellites, start to decrease. And as the agent makes decisions, you can see that some of the satellites decrease, and the agent managed to decrease 2 of the satellites below a threshold, and then finally get the 3rd satellite below the threshold, and that's where we stop the game. And this is the optimal policy. This is close to 17, or close to optimal policy. This is 17 steps for reducing this uncertainty, and you can see that there. We also considered, actually, this is the same case. So if you go and look at this case and you look at the actions the agent has taken, you can see that during the first couple of measurement samples, the agent is equally making observations of all the satellites. And during this window here, starts making observations of just satellite 1 and 2. And then finally, to get to its objective, it needs to go back to making satellite observations of satellite 3. So in this range here, it's making observations of satellites 2 and 3. And we considered a case with a large number of satellites, 30 satellites. And this case was a little more realistic. So what we did is we added propagation gaps. So in most cases, when you have a sensor, you might need to propagate their orbits over time because of daytime constraints. So we added a small propagation gap here, about an hour. So the satellite, or the agent's allowed to make observations for this period, which is 10 minutes. And then at this point here, there's an hour between this point here and the next point. So as you can see, as it's making observations, it's decreasing some of the uncertainty in some of the satellites, but it can't observe all of the satellites due to the limited number of observations. So some of the satellites grow in uncertainty. And then those satellites that have larger uncertainty towards the end of this window here, their orbits are propagated over time and their uncertainties become fairly large over this propagation gap. But then the agent learns to pick up those satellites with large uncertainty and decrease them, and overall decrease the entire catalog until it achieves its objective. So where are we heading with this? So this was a simplified case in data. Where we're heading with this is, can we implement this in the real world, right? So can I set up a telescope and ask the telescope to maintain a list of catalog objects and then give it reward based on how well it can predict? So the telescope makes observations today of objects in its catalog, and then tomorrow, how well are you doing in predicting? What's the measurement residual? And that's your reward. If your measurement residual is high, you're going to get negative reward. If your measurement residual is low, you'll get positive reward. And then the agent over time should learn how to task these sensors. And what you could do with a setup like this is set up a network of sensors that teach each other. So the network of sensors all download this data. This is the set of actions that I perform. This is how well I did over time. You can update your parameters based on that. So you can update the parameters of all the agents based on what they're doing in terms of collecting data. So this is really where we're heading. We want to apply this to real data scenarios. Right now it's all simulation. But can we learn from real data how to task this problem correctly? And more importantly, we can make very general statements on the reward. I can make a statement on, I want to be able to determine the stability of these satellites over 5 days. And you're not going to get a reward if you can't do that. Some of these cases are not solvable, but you get my point. You can make these general statements on what the reward is and learn from real data scenarios on how to perform that. And that's the real benefit of reinforcement learning over other approaches. You can do this with real data. And then just to summarize here, we use the policy gradient method to solve the reinforcement learning problem. We considered 2 simulation cases, one with 3 satellites, one with 30 satellites. The first case did very well, very rapid reduction. The second case, not as fast, but this case highlighted the examples of not having enough sensors to observe the particular satellites we were looking at. And for future work, we want to study the multi-sensor problem. We want to consider contributing sensors. What if sensors are not following my policy? Other sensors that are not following my policy but are giving me data. How do I find a policy to work with that? Well, I need to predict what they're going to do so then I can perform action. So that's a very interesting problem that we're interested in. And then we're looking at agents that applying this agent, what if we apply this agent to solve other missions? How well will this agent work in solving other missions? Data-driven reward is what I talked about before. And one thing that we don't have right now, but definitely we're going to try to do is compare this to other methods. So hopefully this gives a nice overview of what we've done, and I think that concludes my talk.
Roberto.
Yeah, hey, Richard. Interesting paper. I guess my question is, as this progresses and learns, does this algorithm become more rigid in its ability to adapt to new situations? Do you kind of always keep kind of on the side this hypothesis of maybe the thing is behaving in a way that's unexpected to keep yourself from kind of, because as we learn, we tend to become biased.
Yeah. That's a good question. So I think that that's an open-ended question in reinforcement learning. So what if my environment is changing? What do I do? What if right now the best way to observe satellites is totally different than what it's going to be 5 years from now? Excellent question. I don't think that that's solved by this. Someone else have a question?
Quick question.
So in your reward function, you have that gamma parameter that's less than 1. Why are you assuming that actions in the future should give you less reward than the current time step?
It's standard in reinforcement learning, and the reason to do that is if it allows you to consider infinite horizon. So I can play this game as long as the agent doesn't achieve my objective, right? Of course, I'm not going to do that in simulation. I can put off a threshold. But if you have an infinite game, it's basically a discount factor. So locally, I want to be close to optimal. It allows me to play an infinite game, and that reward function doesn't blow up, right? If I let k go to infinity, that value should be infinite.
Really quick.
So I know you had a comparison to other methods there as future work, but I was wondering if you've tried comparing it to any just really naive methods, like always just pick the object with the highest covariance and test against that to get a feel for how well you're doing?
That's exactly what we have to do. So myopic methods that look at right now, what's the best object to observe that will they'll maximize the covariance. I have those implemented. I need to do a proper comparison with our method. One thing I would say is for certain cases, we might do as well, or they might do better, since they might have analytical representations. But I think for cases that you need to plan, cases that you need to, it's not directly obvious right now, because this object has high area to mass ratio and its uncertainty is going to grow. There are methods to do that. There's, Lopinoff exponentials and things like that. But I think this approach will work well there.
This paper could have been titled Track Deletion or Track Confirmation Problem for Orbiting Space Objects. But this is how the problem was originally stated to me some months ago. Let's see. I have to, okay. All right. So space objects in a surveillance catalog are really tracks or orbit estimates. And they could be generated by a tracking system like JSPOC, or what was JSPOC. Or they could be an analyst object where an analyst may have some uncorrelated tracking data which he wants to associate with a particular track, but it may or may not correlate well. And if it doesn't correlate well, it could be because the track is not a valid track. So the objective is that we want to develop an algorithm for track or estimated orbit validation, and then the other objective of this talk is to demonstrate it with some simple simulation results that are illustrative. Now, we could solve the full multiple hypothesis tracking problem, but that's computationally intensive and requires a lot of data that maybe we can't get our hands on, at least for our application. But a faster algorithm is warranted, and that's what I'm going to present. So let me introduce the data association problem in a simple way. It's called a traveling salesman problem. Let's say we have a list of, that's the red button. All right, let's say we have a list of tracks and a list of observations, and there's some score function for each pair of track and observation that is in some way some kind of measure of how well they belong together. And there are a number of scores that have been proposed for this particular travel and salesman problem. Mahalanobis distance or modified Mahalanobis distances between tracks and measurements, various information theoretic measures, and even probabilities. If you go back in the literature far enough, you'll find that. Now, what I'm going to say doesn't detract from any of the earlier papers because they do use information theoretic measures, but they're solving a different problem. The nearest neighbor matching problem is also called the greedy selection problem, and it'll find a match with the lowest score, and then the next match with the next lowest score, and so on. It's virtually guaranteed to be suboptimal, so there's no need to use that algorithm. The global nearest neighbor solution gives you a set of unique matches denoted by this vector m, index vector m, for which this summation is a minimum. It gives you minimum sum of matching scores for each target j and the match for the observation that belongs to it. But in the formulation I've shown you so far with that association matrix, the GNN itself is also suboptimal because, one, the score matrix doesn't account for spurious measurements or new tracks, and the choice of the scores is arbitrary. But you can find this kind of stuff in literature, and if you go reading it, you might be a little confused as to what they're trying to do. So let me give you a quick overview of the track validation algorithm before I give you any of the details of it. First of all, we obtain some observation data and select tracks or orbits which are in the field of view of the tracking sensor. And then for each frame of observation data, we'll compute a maximum likelihood association or non-association of observations and tracks. And that is to say, if you go back and look at this, this matrix as written requires you to have an association of track and observation. You can't have a track with no association or observation with no association, and that's why it doesn't work very well. So you compute the maximum likelihood association, then update a sequential likelihood or log likelihood ratio for each track, and then compute the probability that a track is valid from its sequential likelihood ratio. And then you do a little test. If the probability is sufficiently close to 0, you'll delete the track from the catalog because it's invalid. Or if the probability is close to 1, you'll confirm the track. All right, now let's focus on these 4 hypotheses in the box at the top. D1 is the hypothesis that we've detected a space object that is supposed to correspond to our catalog track. And D0 is a hypothesis that we didn't detect it. H1 is a hypothesis that the track is valid. And H0 is the hypothesis that the track is invalid. Now we will calculate probability densities of the data joint with the detection hypothesis, given that the track is valid or invalid. And using Bayes' rule, that can be written as a product of 2 probabilities. So we have 4 combinations of these probabilities: detection in invalid track, not detection of a valid track, detection of a space object when the track is not valid, and non-detection of a non-valid object. Now this one may seem to not make physical sense, and there's discussions about that in various places in the literature already. But it's a useful mathematical construct for us. So we'll define these 4 test statistics, one of which is the difference between our observation and the predicted observation, sometimes called a residual. By the way, the track cannot have been updated with this measurement, otherwise it's not independent. So we have to assume we have some independent observations. The other test statistic is the track itself, and that's in the case where you don't have a detection, so there's no measurement for it. The third case is where you have a measurement but no track to go with that measurement. And then for the fourth hypothesis, That's the estimated position again, or position and velocity, whatever you're measuring. And then for each of these test statistics, there's a density function defined. The residual is given by a normal density function times the probability of detection. If you have a track with no measurement associated with it, that's a diffuse density function, times 1 minus the probability of detection. And then the other two are defined also. So in the interest of time, I'll not talk about those too much. Now let's look at some likelihood ratios. By the way, the indexes of the P's are suggested it's going to go into a matrix, and indeed we will put it into a matrix. And I'll show you that later, because if I show it to you now, you may not appreciate where it comes from. And that was one thing I found in this paper, that I was wondering why I couldn't find this in literature, and I kept digging and digging, and eventually I found it. A track deletion algorithm by Blackman. However, I took a totally different approach and made it a little bit more general than what he had done. So take some likelihood ratios of the density of the data in the case of valid track, and you have detection versus the data in the case of a valid track and non-detection. And then the other likelihood ratio is the joint density function of the data with detection and invalid track, and the joint density function of the data in the case of non-detection and a non-valid track or invalid track. So we form these likelihood ratios and then test them. If this one's bigger than that one, we will say that the detection is more likely under H1 than H0. That is, detection is more likely in the case that the track was valid than if it was not valid, which would obviously say that we probably detected a space object that's really there. The other one would say we detected something, but it's not a space object corresponding to our catalog track. Now we cross multiply terms, and so the test becomes this expression. Now what we want to do is compute a joint density function of our data, because we have multiple tracks, multiple measurements. And so this is a product for each of the tracks of the probabilities, density functions, assuming some combination of tracks and measurements or non-associations. And what we want to do is maximize the, or calculate the maximum likelihood association of the data. And we do that by maximizing this density function. It might seem a little bit abstract, but hypothesis testing is a little bit abstract by nature. And you could consider a maximum a posteriori solution, but the problem is you don't have prior statistics on the associations. And you may have some for some associations, but not for the others, so that's not worth calculating. Now, equivalently, you can maximize, or minimize, that is, the negative log of this joint density function. So you get the negative sum of logs of the density functions. So we have the maximum likelihood solution being the association vector phi, which minimizes the negative log of the joint density function. And again, that's given by a summation right here. Now we get to the, getting close to the score matrix. We'll call this thing, for the moment, just a hypothesis matrix. You can think of it as a score matrix. But in the top row, we have densities corresponding to a valid catalog track in the cases of detection and non-detection. And then in the bottom row, For an invalid track, we have density functions in cases of detection and non-detection. So this is our score matrix. And what's different from what you find in most of the literature are all these additional columns in here. The I don't want to call it classical. The G&N solution I showed you earlier would just have this upper left block in it. So this gives you the ability to make non-associations of tracks and measurements. Now for track validity, we take a likelihood ratio of the density functions for detection given that the track is valid versus invalid. And that can be written as a product, as I showed you earlier. And then if you notice, the ratio of the terms on the right can be taken from a prior update of the likelihood ratio. And so we multiply it by this term on the left, which I'll call C. And C is, under the case of detection, given by this ratio, which involves that normal density function. Lambda sub s is the spurious measurement density. In the case of non-detection, depending on what our inequality or our assignment solution gave us, we have this likelihood ratio. Now, in contrary to a paper presented just a little while ago, this bottom term is cumulative evidence that the target doesn't exist. And so if you go long enough without having measurements that correlate strongly enough to the track, you'll declare that to be an invalid track. Now, it may be that your noise in the measurements or tracks are large enough that these ratios are close to 1, in which case it won't give you a decision, at least maybe not for a long time. So the sequential probability ratio test, which is pretty classic using likelihood ratios, compares the likelihood ratio against this upper and lower threshold. And you can write this in terms of log likelihood or probabilities, and both those are in the paper. And this example is shows 4 tracks. The middle one is not measured, and the diagonal one is not measured. And the numbers on there are the probabilities and the scores for the association. And what happens, I'll just describe what happens because it's hard to read. The likelihood ratio will start, well, I started out at 0.5, which is, the probability of valid track at 0.5, which gives you a likelihood ratio of 0. So I start lambda at 0. As you have measurements which are close to more than one track, this likelihood tends to rise a little bit, and then because we're not measuring this diagonal one, it goes back down to 0. And then eventually the SPRT test will declare it to be an invalid track. For these, the probability went to 1, and for the top track and the lower one. And then for the middle, it went to 0. And those are plotted on the next page. I plotted likelihood ratios and the probabilities. We'll just look at the probabilities, I guess. These two went to 1 as they should, and these went down to 0. This one took a little longer. I think that was the middle track. As I mentioned, there's a chance that you could have large noise or large error in the track, in which case this likelihood ratio will continue on for a long time. Not presenting it here, but in the paper there's also equations that help you choose the parameters, and that's a different method than what you'll typically find in the literature. This track validation algorithm will compute the cumulative probability that a track is valid or invalid based on observation data, and it doesn't require a lot of computation. It's based on some rigorous derivations, so there's nothing ad hoc in there. Also, I don't use subterfuges of pseudo tracks or pseudo measurements. I got away from that. You can find that pervasive in the literature on this subject. And then, as I mentioned, there are formulas in the paper for driving these tuning parameters to ensure proper operation of the algorithm. And there are only 3 of them. 2 of them you can set equal, actually. And then there's ambiguity resolution considered in the paper, where if you have 2 tracks that are crossing and you have measurements for both, there'll be some ambiguity in the association of the data with the tracks, and you want to be able to handle that. And then I ran a lot of Monte Carlo simulation results, which are shown in the paper.
Okay, thank you very much. So just to elaborate on the title, by high performance, in this case I mean GPU computing. By orbital propagation I mean analytical orbital propagation, at least for now. And by generic software architecture, I mean an architecture that allows you to use a propagator as a plugin into a host application. The GPU computing becomes more and more popular at the moment. So most of you may already have heard it, but I'm just going to go into the basics quickly, go into the software architecture that we developed, and I'm going to introduce 2 GPU-based analytical propagators. Up to this point, this is all based on work that I did back at the Institute of Space Systems in Germany. Now at Zurich, what I'm trying to do is use the same techniques for conjunction assessment, and that's what I'm going to finish with. So if we look at graphics processors in their original use case, which is video games, obviously, they're used in a way, so these games work like there's a 3-dimensional geometry built from a set of vertices, which you can see on the left side here. And based on that geometry, an image is generated, which is basically a set of pixels. Each pixel has a certain color, which is based on this 3-dimensional scene. And in both of these stages, the vertices and the pixels, respectively, can be processed independently from each other. And that's the reason why graphics processors are designed for massive parallelism. If you look at this illustration of the architecture here, we can see that for a classic GPU, the control section is much larger, meaning that it is able to run more versatile calculations, whereas the GPU focuses on a very specific set of tasks, but dedicates a lot of the transistor space to ALUs, which means that it can process a lot of data in parallel. In particular, the model that these architectures are based on is called single instruction multiple data, which means that the same algorithm is executed on a large set of data. So every vertex, every pixel runs through the same algorithm, and this works very well for space applications too. If we have a large satellite population, if we want to propagate it, we can use the same algorithm for all of these objects. There are certain types of languages that are specially designed to program GPUs. The ones that can be used for general purpose computing are CUDA and OpenCL, both of which I've used in the programs that I'm introducing here. And what you have to keep in mind when you're using GPUs for scientific applications is that they're optimized for single precision floating point, because video games don't care about high accuracy, but scientific applications do. So all of the GPUs are able to calculate in double precision, but it's usually a lot slower. So that's something that we have to keep in mind. If we look at orbital propagators from a software architecture point of view, then there's certain things that usually come up. The first thing is that the propagator is usually a part of a larger software application. It's a critical part, both in terms of accuracy and performance. But usually it's something that's developed independently and sometimes even by different people. So we want to keep that separate from the host application. The propagator itself, sorry. The propagator itself usually consists of a number of perturbation models, which are themselves independently developed and integrated. So ideally, we want to have the propagator itself modular. And in case of GPU computing, what we want to achieve is to hide the extra complexity that comes from hardware controls and memory management from the user or the writer of the propagator. This is why we came up with the orbital propagation interface. This is a dynamic library. It's published as open source, so everyone's welcome to try it, make it better even. It allows anyone to build a propagator as a plugin that can dynamically load it into any host application at runtime. So we have interfaces for the host, we have interface for the propagator, and any program that uses the host interface can use any propagator that uses the propagation interface. The communication is done via this population object, which holds a population of satellites, and it also does data transfer automatically. So if the propagator uses the GPU, then this population object will transfer the data automatically to the GPU as needed. Then there's this propagator module, which can be used to modularize the propagator itself. So it's even possible to build a propagator out of a certain number of perturbation modules at runtime. It supports different languages, so C, C++, Fortran, Python, and CUDA at the moment. Host and propagator are independent, which means that you could, for example, use a Fortran host and a C propagator if you wanted to. I've used this interface to port an analytical propagator that we used at the Institute of Space Systems. It's called, it's called Flora. This is a propagator that we use for long-term analysis of the space debris environment. We've been looking at time frames of 200 years and object populations of several 100,000, which means that we need a very fast propagator. But since we're only doing statistical analysis, it doesn't have to be dead accurate. So this is good because this means that I could use single precision floating point and achieve higher performance with only minor accuracy loss. It's based on fairly standard perturbation models, which are all implemented independently using the interface. These are a couple of accuracy results. So compared to the original program, which is written in double precision throughout, we only have a minor loss of mainly semi-major axis of about 2 kilometers in 50 years typically, which is very much acceptable if you're just doing statistical analysis. As for performance, the original implementation is down here with about 130,000 propagations per second, whereas on the fastest GPU that we had available, the GPU port performed at 7.5 million propagations per second, which is a speed-up factor of about 60, or in other words, the work of an hour could be done in a minute. It is also notable that every newer GPU generation performed significantly better than the one prior to that, whereas in the CPU area, there's not much of a performance gain. We also use the same propagator for visualization. This is an image from a visualization software that I've seen on other slides in this session already. Using this GPU-based propagator, it was possible to animate 110,000 objects at 60 frames per second with all perturbations enabled. Just for comparison, I mentioned that GPUs are optimized for single precision accuracy. If we do the same in double precision, obviously we get better results. But we have a significant drop of performance, so whenever it's possible, even in parts, to use single precision instead of double precision, then it's almost always worth to look into it. The only card that performed about the same, whether it was single or double precision, was the NVIDIA Tesla, which is a card that is specifically designed for scientific applications, but it also costs 10 times as much, and it becomes obsolete just as fast as regular GPUs. So this is an option if money is not an issue. I also ported the SGP4 propagator to OpenCL this time, which means that it runs on a greater variety of parallel platforms, including multi-core CPUs. In this case, the speed up compared to the original implementation is not as high. That's because we use double precision and not single precision. But the OpenCL implementation means that we can run it on any 8-core processor, like in this case, which even outperforms one of the slower GPUs. But the faster one is still significantly faster in this case. So getting to conjunction assessment, these are very promising results. So what we're trying now is to apply them to conjunction assessment as well. And this is a performance result of a very simple first stage conjunction filter, which compares the perigee and the apogee heights of two objects, and based on that decides if they are close to each other and are potential candidates for a collision. Using this simple filter on the CPU, generated about 26 million conjunction checks per second. On the GPU, we got to 860 million conjunction checks per second, which is obviously significantly better. The only problem that we have in this case is, since we're using a single instruction multiple data architecture, we generate large amount of intermediate data. That's because if we're using the CPU, then we can just grab an object pair, apply a filter to it. If it passes the filter, use the next one, and so on. On a single instruction multiple data architecture, what we have to do for best performance is we have to run all the objects through one filter, then take the remaining objects, run them to the next filter, and so on. So there's a bit of memory management involved that we have to do in order to not exceed the memory of the GPU. This is a runtime analysis of the current conjunction assessment software that we're using, the one that runs on the CPU. I found that about 70% of it is parallelizable. So if we could speed up the filtering, so the pre-filter stage, the in-depth filter stage, and the propagator, we can achieve a great overall speed up, especially in the pre-filter, which takes about half of the overall runtime. If we can speed this up, we can achieve great results. On the GPU, there's a bit of a difference because the pass rate plays a role in the performance of the filter. So every time we have to write an object from the filter, then this is very slow. So a filter with a smaller pass rate will always perform better than a filter with a low pass rate because of the write operations. But also a more complex filter that may filter more of the objects may run slower because it's more computational expensive. So it's very important to just find the right balance between the pass rate and the complexity, which is another another added problem that we have when we're using the GPU. Still, in this case, so far we were able to reduce the runtime for our weekly conjunction assessment analysis from about 20 seconds per propagation time step to about 0.8 seconds per propagation time step. So we can generate conjunction assessment analyses significantly faster on the GPU. In conclusion, I've just said it, GPU computing can significantly speed up many space research applications, especially if we can sacrifice some accuracy and use single precision instead of double precision. I've talked about the overhead that the new architecture generates. This can be hidden from the user or the person who implements the propagator or the conjunction filters within a feasible software architecture. That's all I have. Thank you very much.
Questions?
You mentioned at the very beginning of your talk, this is an analytical solution, and you were looking perhaps in the future into moving on to more numerical differential equation solvers. What challenges do you foresee in that step forward?
I think that the main challenge will be finding an ODE solver that will be up to the task. Specifically, if we have variable step numerical propagators, this will be a challenge because it doesn't fit into the single instruction multiple data paradigm, and some of the objects require more time steps than others. What we could do there is to sort the objects. So if we do circular orbits first, which are likely to have the same amount of time steps, and then the more eccentric orbits, which may have more time steps, that might be a solution. If we could find a propagation algorithm that works well with a fixed step numerical integrator, then this would be another solution. I've seen very fast implementations of the Runge Cutter integrator, for example, on GPUs. So if we could use that, that would make things much easier.
What's the learning curve on the CUDA and OpenCL?
You mean the differences between the two?
The learning curve on
the learning curve, sorry. So they're both very similar, which means once you've learned one of them, it's very easy to get to the other. Otherwise, it's just a programming interface. Both are very well documented. So if you know software development, then it's pretty easy to get into it. But since it's a very new field, means that those APIs are still changing a lot. It's getting a bit slower, but the code that I wrote when I started all this research was significantly different from what I ended up with because of the changes in the APIs, but it's beginning to slow down, so I assume that it's going to get easier from now on.
Any other questions? If not, let's thank the speaker.
Thank you.